When working with rational functions, we'll always first see if we can find a removable discontinuity or hole in the graph by checking if any factors reduce. So remember, that's how you find the removable discontinuities, is finding a common factor that reduces. So in number 3, we have this rational function g of x. If we graph it in the calculator, it looks something like this. Notice it looks like there's a vertical asymptote here, and it doesn't look like there's much else going on. But if we go to try to find the discontinuities, remember you set the denominator equal to 0. So we're going to try to factor that and set it equal to 0 and solve. So you can pause the video and try that. I'm going to show you the answer. Okay, so we know that the denominator factors to x minus 2 times x plus 6. Notice that x minus 2 is a common factor, so that means that reduces out. Now when you reduce that, remember you still have a 1 in the numerator, and then the denominator has x plus 6. So which values are restricted from the domain? The x minus 2 will give you x equals positive 2, and x plus 6 gives you x equals negative 6. So those are the two values that are restricted from the domain. So the next thing we want to look at is, we saw on the graph that it looked like there was a vertical asymptote at negative 6. But when x equals 2, we don't really see what's happening. It almost looks like your graph stops. But remember, your calculator just can't draw that function going out farther and farther to the right. So if I press trace and enter 2, notice it gives me nothing for an answer. It doesn't mean 0. It means that it's undefined. So there's something happening here at x equals 2 that your calculator can't quite draw. So what we want to do is we want to examine what's happening to our graph or our function as x approaches 2. So I've created this table of values of 1.9, 1.99, and so on. So coming from the left-hand side of 2, and then from the right-hand side of 2 if you come from the bottom up in the table. So if we fill in that table of values, one way you can do that is you can press trace and then enter the values in. So if I enter 1.9 and then press enter, it brings me to 0.12658. And then I could put in 1.99 and then press enter. And that'll give me the next value in the table, and I can do it that way. The other way you can do it is you can go to second table set, and then you can scroll down to independent. That means your x variable. Highlight that. And then when you go to the table, second graph or the table, you can enter whatever you want in. So 1.9, and then 1.99, and so on. Now I like to just use the graph with the trace feature. That's just my preference, because then I can see where it's going on the graph. But either way is up to you. So take a minute and try to fill that in, and do the same thing when x approaches negative 6. Okay, so you want to fill in that table. And I'll put the answers up. So here are the tables when you enter the values in. So as x approaches positive 2, it looks like from the left-hand side, it's getting closer to 0.125. And then from the right-hand side, also getting closer to 0.125. And then when x approaches negative 6, notice what's happening here. As you get closer to negative 6 from the left side, your y is getting lower and lower and lower. So what's happening there on the graph is as you approach negative 6 on this left-hand side, notice how it's getting lower and lower and lower. On the right-hand side, as you approach from negative 6, it's getting higher, higher, higher. So it's getting larger in the positive direction on the right-hand side of negative 6, and larger in the negative direction as you approach negative 6 from the left side. So what is happening as far as discontinuities for g of x? Well, it looks like as you approach 2, the y value wants to approach 0.125. When x equals 2, it's undefined, but as you approach 2, it looks like the y value wants to approach 0.125. And as you approach -6, that has the vertical asymptote or infinite discontinuity at x equals -6. Okay, so now we're going to look at the behavior of g of x as x approaches 2. So this is just kind of formalizing what happens in the tables here and what happens with the discontinuities. So as x approaches 2, so this notation here, as x approaches 2 from the negative or the left side, what is y approaching? Well, y is approaching 0.125. And that's what we said. As you approach 2 from the left side, so at 1.9, 1.99, and so on, we're getting closer to 0.125. This notation, that little negative sign, notice it's not in front of the 2 to say -2. A lot of students make that mistake. That little negative and this little positive aren't telling you the sign of the number. It's telling you which direction you're approaching the value from. So here we're approaching 2 from the left side, and in here we're approaching 2 from the right side. And both of those are approaching 0.125 for the y value. So using limit notation, as x approaches -2, I just made that mistake. As x approaches 2 from the left, our g of x function approaches 0.125. So this is the notation of how you write this concept. Okay, and same idea for approaching 2 from the right side. And then as far as the behavior, as x approaches -6, well, from the left side of -6, y approached -infinity. So from the left side, that gave us the -1,000. If you put another 0 and then the 1, you would have -10,000. So notice how that's getting smaller and smaller and smaller, or more negative, as you approach -6 from the left. And then from the right side, the y value is approaching infinity, so it's getting higher and higher. So using the limit notation, that's how you write that. So then looking at the behavior of g of x as x approaches positive or negative infinity. So this is looking at the end behavior of the graph. So on our calculator, it's hard to see that. So what we're going to look at is, if you look at our function and put in large positive values. So if we look at our function, and I always find it easier to look at the original. If you put in a large value, like say 100, you would have pretty close to 100, technically 98, divided by 100 squared. You have the numerator much smaller than the denominator, so that is going to 0. And in our calculator, as you trace out to the right, your calculator just can't draw it. Okay, we could zoom in some and we could get a little more of the graph. But what's happening is you go way out to the right, you're getting closer and closer to 0. On the left end, the same idea. If you put a negative number in for x, like -100, if you do -100 divided by -100 squared, you would have a smaller number divided by a much larger number. But it would be negative. So that shows on the graph as approaching from the bottom of the x-axis. So y is approaching 0 from the bottom side or the negative side. So using the notation, what's happening here as x approaches infinity, the y value is approaching 0, and as x approaches -infinity, the y value is also approaching 0. And then here is the limit notation to write that. So now we want to sketch a graph. And our calculator, again, this is where we need to outsmart what's happening on the calculator. We can see the vertical asymptote here at -6. at x equals -6. But we can't see what's happening right here. So this is where we really need to understand rational functions. We have a whole or removable discontinuity at the point 2, comma 0.125. So that's occurring over here. So you sketch a version of that graph. And then if we look at rational functions, remember that removable discontinuities are always found by canceling a common factor. Let me go to the vertical asymptotes, or infinite discontinuities, may occur at values of x for which the function is undefined. So that is when the denominator equals 0. However, you must be careful of the removable discontinuities. So if a factor canceled out first, that shows you a removable discontinuity, and then the vertical asymptote will be where the denominator is 0 for all those leftover factors. So get rid of the common factor first by reducing if you can, and then the vertical asymptotes are what's left over when the denominator is 0. And then the horizontal asymptotes, they're found by substituting very large positive and negative values for x. So if the function approaches a real number, then that real number is a horizontal asymptote. So that's where you use that limit notation, or as x arrow infinity, y arrow blank. So that's that notation. So number 4, we just have a couple examples here that I want you to try, and I'll put the answers up. So here's the first one, 3x plus 4 over x minus 2 equals f of x. So notice that nothing reduces out, so there's no common factor, so there's no removable discontinuity. And then we see the vertical asymptote at x equals 2. And then, as the x value gets very large, so for example, if you put 100 in for x, you would have 300 divided by 100, which is 3. If you put 1,000,000 in for x, that'd be 3 million divided by 1 million, which is essentially 3 again. So we see the degrees there are equal in the numerator and denominator. And so what happens is you just take the ratio of the leading coefficients. So y equals 3 is your asymptote, horizontal asymptote. Hey, and we can also find x and y intercepts. X-intercept, you set the numerator equal to 0. So you get -4/3. If you look at the y-intercept, you put 0 in for x. So if you cover the 3x and x, you have +4 over -2. And that gives you -2. So the y-intercept here is at 0, -2. And then here's the last one, h of x. There is a common factor in that one, which means there's a removable discontinuity in the graph at -5. And we see when x is -5, we get a hole in the graph. And again, with the calculator, when you graph it, it may not show up. Or I shouldn't say may, it doesn't show up. So make sure that you pay attention to that. So we just have our basic graph of y equals 1 over x, except when x equals -5, there's a removable discontinuity in the graph. So vertical asymptote is x equals 0. Horizontal asymptote is y equals 0. So when you put large numbers in for x, so put like 100 in, you'd have 100 divided by 100 squared, which goes to 0. Same thing if you put a large negative number in, you get close to 0, except from the negative side. And then the whole, or the removable discontinuity, when x is -5, notice now if you substitute -5 into this reduced equation, or reduced expression, you get 1 over -5. So there's the coordinates of the removable discontinuity.